Let's begin with the next question. Here we have a question dealing with conservation of momentum, energy, collisions, and elastic potential energy. So let's take a look. A block of mass 2m rests on a horizontal frictionless table and is attached to a relaxed spring. So as of now, we understand that block 2m is in a position of rest. The spring is non-collinear and exerts a force f of x equal to minus bx cube. So the force exerted by the spring when compressed is f of x is equal to minus bx cube, where b is a positive constant and x is the displacement from the equilibrium for the spring. A block of mass 3m and initial speed v0 is moving to the left as shown. On the dots below, which represent the blocks of mass 2m and 3m, draw and label the forces that act on each block before they collide. Each force must be represented by a distinct arrow starting on and pointing away from the appropriate dot. Here I know that block 2m is in a state of rest, so there are no forces acting towards the left or towards the right, as it is also indicated that the spring is in a relaxed position. So the only forces acting are its weight, mg, which is 2 times m into g, acting downwards, and its normal reaction force, normal or reaction force, and let's call it n1, acting upwards. Block 3m also has its weight 3m into g, acting downwards, and its normal force n2, let's call it, acting upwards. Since it is not indicated that the initial speed v0 is changing, we shall assume that there are no forces acting towards the left or the right. Let's move on. And before we move on to the next part of the question, it is also indicated, or in fact, it is not indicated that the surface is or does have friction. So we will assume that there is no friction or frictional force acting to the right. Next, the two blocks collide and stick to each other. The two block system then compresses the spring a maximum distance d as shown above. Express your answers to parts B, C, and D in terms of m, b, v0, and wherever physical constants are appropriately used. Let's first answer part B of the question. Part B asks us to derive an expression for the speed of the blocks immediately after the collision. So as indicated in our free body diagrams and also from the sentencing or the framing of the words in the question, it is obvious that there are no external forces involved. So this concludes to us assuming that momentum is conserved. Momentum is conserved. Since momentum is conserved, this means that the total momentum of the two bodies, 2m and 3m before collision, is equivalent to their momentum after collision. So before collision, block 2m is at rest, so no momentum there. Block 3m is moving with a momentum. By the way, momentum is given by the formula. Momentum P is equal to m into v. It's a product of mass into velocity. So 3m into the velocity is v0. This is equal to, after collision, I know that the bodies stick together. So 3m plus 2m is considered as one single body whose velocity, let's call it as vf or v final. I can rewrite this equation in terms of vf as vf is equal to 3 divided by 5 v0, as m gets cancelled on both the sides. Moving on to part C of the question. Part C tells us derive an expression for the kinetic energy of the two block system immediately after the collision. So the kinetic energy of the two block system or any system in general is given by the formula kinetic energy Ke is equal to half into mass times the square of velocity. Here, after collision, the bodies stick together. So the combined mass is 3 plus 2, that is 5m. And their velocity, which is v final, here it becomes half into 5m into v final the whole square. V final the whole square is 3 by 5 v naught the whole square. We need to substitute this as they want our answers to be expressed in terms of v naught and not vf. So 3 times 3 squared is 9, 5 squared is 25, v naught the whole square. 5 times 5 cancels here. This gives us the answer as 9 over 10 capital M v naught the whole square. So this is the value of kinetic energy of the system after the collision. Moving on to part D, derive an expression for maximum distance d the spring is compressed. So as the bodies stick together after collision and they compress, I know, or we know, the kinetic energy of the two bodies is what helps compress the spring and in turn store the energy as elastic potential energy. So in other words, conservation of energy applied here tells us that the kinetic energy of the system of bodies is converted to the elastic potential energy of the spring. And we know that there is no loss of energy because there is no mention of friction or an indicative of any other resistive forces present in this scenario. So kinetic energy is 9 over 10 capital M v naught the whole square. This is equated to elastic potential energy. I know that F here is given by minus bx square, f of x. I also know that the elastic potential energy U is equal to minus integral of f dx. This equation specifically applies for a conservative force when there are no external forces involved, as is the scenario in this particular question. So going ahead from here, we get to solve this and we substitute minus integral. By the way, for the integral for dx, which is a derivative of length, the limits are 0 to d as indicated here. So 0 to d, f of x is minus b x cube dx. Minus of minus becomes plus. So 9 over 10 m v naught the whole square is equal to b into integral of x cube dx follows the general pattern. Integral of x power n dx, which is x power n plus 1 by n plus 1. So you get x power 4 by 4 under the limits of the definite integrals 0 to d. I know that I can simplify here as 2 over 5. And they want an expression for maximum distance d. So I know the equation can be rewritten as 9 over 5 m v naught square b into d power 4 by 2. This is the expression. And when rewritten in terms of d, we get d is equal to 9 into 2, which is 18. Let's write 18. 18 m v naught the whole square divided by 5b whole under a fourth root. So this is our solution for the given question. Thank you.